In Module 2 of Chapter 20, we're going to look at a Brownian motion, which is that mysterious dz term in the stochastic price process 20.1 that we were looking at earlier. So Brownian motion is basically a continuous version of a random walk. We've seen discrete random walks before where we hypothesized that we might be flipping a coin, and with every coin flip, a head being a +1, a tail being a -1, we could generate a series of z's where we looked at z's as a summation of yi, and the yi was a coin flip being a + or -1, and then we could look at this z sub n, which would be the sum of n coin flips, and we had a discrete version of Brownian motion. Here, we're going to try to take that notion to the limit, and that will give us, in fact, the Brownian motion. The idea is, in this earlier example, each coin flip was a +1 or a -1. And what we'd like to do is to let n go to infinity, but in a sense, we want each coin flip to represent the movement of the value that's appropriate for an ever-shrinking period of time. So if + and -1 were the appropriate coin flip value for a period of length 1, we'd like to change this coin flip example so that the y values depend on h, the length of the interval, and that in general they have the appropriate property that as the interval gets smaller, the + and -1 values will also get smaller. And that's what ultimately is going to give us Brownian motion, but we need to control how quickly the y values get smaller. And let's see what that means. Well, z of t, which is the definition of Brownian motion, will have some properties. And I will tell you at the outset, they are properties that seem reasonable, but it's by no means a simple feat to actually formally justify that this exotic creature called Brownian motion actually exists. And the mathematics to prove that it exists and has the properties that we're going to list, the mathematics is fairly advanced. So some of this you are being asked to just take on faith that there is a mathematical framework that formalizes this, and but I think that intuitively it's not hard to believe that such a process might exist. So z of t is for each t a random variable, and it's intuitively this random walk where we flip coins after very short periods of time and add a plus or a minus value. And the properties of this is that we start at 0. By convention, Brownian motion starts at 0. It doesn't need to, but typically it's the right place to start. It's going to be a continuous. Those two are not hard to imagine. Continuous function that starts at 0. A couple of other properties of Brownian motion are that if I look at any interval of time from t to t plus s, the change in this process is a random variable. Each one of the z's, remember, is a normally distributed random variable, but that the change is normally distributed, and it has a mean of 0. No matter what interval I look at, the average change of z is 0, and the variance of those changes is the length of the interval. So in particular, if I let t be 0, it's saying that the change from time 0 to time s is normally distributed with a mean of 0 and a variance of s. So this, we can let t be 0, and we get the change from 0 to s, or we can let t be anything we want. So it's saying that the change in this process over every interval is normally distributed, mean 0, and the variance is predictable by the length of the interval. Moreover, this last property requires that over any two intervals that are non-overlapping, the change in the z value are independent normal. Each one of these changes in z from time t to time t plus s1, that's normally distributed. We also know by the third bullet that the change from time t minus s2 to t, that's a normal variable with a predictable variance. What bullet 4 says is that these two normal random variables are independent.